So now let's go to part 2, where I can use a shunt capacitor. So use capacitor. And I have my ZL. And I'm going to add a shunt capacitor. And my goal again is to bring ZL to Z0. All right, and the question is, what region of the Smith chart can I actually use a capacitor as a single element matching network? Okay, this is what we're looking at right now. We're looking at single element matching networks. Now the way that, let's think about this. Now, let's actually start not from ZL, but let's start from the other end, Z0. Okay, so I know that I need to bring it here, right? Okay. Now let me be on the Y chart, because from the other end I'm adding an admittance. I'm adding a j omega c. And when I add let's say that I'm now on the Y chart, and I've presented you with some ZL or YL, okay? I presented you with some YL. Okay, let me just say, pick a real thing here. Let's say I'm here. This is my YL. If this is my YL, and I'm adding a j omega c, I'm adding an admittance to it, then which way is this going to move on the Smith chart, on the Y chart?
Clockwise.
Yes, it's going to move that way, because this point here is 2 minus J2, right? So it's a minus, and I'm going to be adding a plus j omega c, so I'm going to be moving this way. And can I ever bring this point? Remember that a match point on the Y chart is the same as a match point on the Z chart. 50 ohms is 50 ohms. 1 is 1. The inverse of 1 is 1. So can I ever bring this to the center? No. So where does my YL need to be then, in order for me to bring it to match? Yes, and B, is it positive or negative?
Negative.
Negative. So isn't it the same one?
Yeah.
Okay, but except, remember, I'm on the Y chart, okay? So my question now is, what does this semicircle on the Z chart look like what does the semicircle on the Y chart look like on the Z chart? Is it this semicircle?
Okay, in the Z will be that.
Say it again?
On the Z chart,
Yeah, so the question is, let's say that this blue circle is on the Y chart. I'm looking to translate that blue circle to the Z chart.
No. I think I like to map your points on this side to the other side in 180 degrees.
rotate that.
Yeah. Do you have any sense of what that might look like on the other side? If you do that mapping?
The same thing, but
Yeah, exactly the same. Yeah, it will look like this. Right? Because, if you map this point to this point, then you map here, right, map here,
yeah.
right? So it just keeps mapping, mapping, mapping. All right, so my ZL, if I'm using a shunt C, has to be here. Okay. Now, does it actually have to be right on these semicircles? No, because we don't design perfect matching networks. we design matching networks in the real world that fall within some VSWR circle. So let's say that my criteria was to have a matching network that would give me a return loss of better than of gamma is equal to, or let's say this circle is gamma is equal to minus 10 dB. Okay, this is by the way, gamma and VSWR, they're I mean, you can get one from the other, right? And I'm just expressing gamma in dB. So so this is typically a criteria, and so it's you might be I might ask, you know, we need to have a matching network that has a gamma that's less than minus 10 dB. That means that you need to be inside this circle, right? So when you match it, you need to get it and bring it inside the circle. So that means that my allowable ZL for the first example here, where I'm using an inductor, is actually not a thin line, but it's kind of a region here. Kind of a region. And the same thing for my ZL, where I'm using a capacitor to match. It's again a region. Okay, so if I have a ZL anywhere here, I can match it to within my specified criteria. Okay. Now, you guys know that that 20 times log in base 10 of the magnitude of gamma is going to be gamma expressed in dB. Right? Okay. So for example, if my gamma is 0.1, then I have a 20 dB. Then in dB it's minus 20 dB. Right? Okay. And from gamma, I can always calculate VSWR. Now, why is it 20? Because it's a voltage reflection coefficient. You can say 10 times log base 10 gamma squared, because now this is a power reflection coefficient. And these are the same, right? The 2 times 10 is 20.